On the last lecture, we discussed the first part of interference, where we discussed what are the essential conditions to observe interference of light. I just summarize it. The essential condition is the waves must be coherent. That is, they should maintain constant phase difference between them. The second, they must have the same frequency. Third, if the waves are polarized, they must have the same polarization. Then there are conditions for good contrast, namely, the waves should have been propagating in the same direction, and that intensity of the two waves should be approximately be the same. Now we proceed to the next part. We have seen that the interference in ordinary light can be observed by two techniques. Number one, dividing the wavefront and dividing the amplitude of the wave train. So, we have read, discussed and understood Newton's rings, which originate from thin film enclosed between a plano-convex lens and a plain glass plate. Now, we proceed on to a very important and versatile instrument named Michelson's interferometer. Michelson interferometer also utilize amplitude divided coherent beams to observe interference. But this instrument is very precise and technologically very versatile. To understand the underlying principle, let us see what happens. Refer to the diagram here. Light from a sodium lamp falls on a fine slit, which is at the focus of a convex lens. The light then falls on a beam splitter. The beam splitter divides this beam into two equal intensity beams, one traveling along the direction of light, say x-axis, and another travels perpendicular to it, y-axis, because the beam splitter makes an angle of 45 degree with the incident beam. The two beams are traveling mutually perpendicular. To observe interference, they should propagate in the same direction. Therefore, reflect these beams by perfectly plane mirrors. The notable feature is that these mirrors should be front coated so that they do not introduce any additional path difference. They reflect the beam back, and the two beams, after being reflected, meet at the beam splitter, which reflects them to the telescope, and we observe interference fringes. Now, what type of interference fringes shall we observe, and why do we observe, can be understood by a simple means. See that this mirror finds its image in the beam splitter at somewhere here. And therefore, looking from a telescope, we find a virtual thin film of air enclosed between mirror M1 and image of the mirror M2. There is a thin film, virtual thin film of air. The light incident on this is reflected from this mirror. It travels to the second mirror and is reflected back. We extrapolate the beams and find that while looking from the telescope or eye, the beams appear to come from these 2 points, say A and B. These are the parallel beams, and therefore we need a telescope to observe them. I have put a telescope here. See that the two beams differ in a path difference delta. This path difference is simply, if I take this angle as r, then this angle is also r, and therefore path difference, this path difference is this distance multiplied by cos r. How much is this distance? It's very simple to calculate. Suppose this distance is d, then image is 8 far as the object, therefore this distance will be 2d. If you can't, you can verify it mathematically by a simple technique. The image in this mirror is here and image in this mirror is here. And therefore the path difference comes out to be 2d cos r. This is a geometrical path difference. This is a geometrical path difference because this beam, one of the beam is reflected from a denser medium C. The beam coming out from mirror M2 is reflected from air glass interface, whereas the beam 2, beam 1 coming out does not suffer a reflection from the denser medium. It suffers a reflection from glass air interface. Therefore, there will be an additional path difference of lambda by 2. So the net path difference is 2d cos r plus lambda by 2. Obviously, for interference maximum, 2d cos r plus lambda by 2 must be equal to n lambda, or 2d cos r must be equal to n minus half lambda. For minimum, obviously, 2d cos r is equal to lambda, n lambda. N is obviously 1, 2, 3, 4 and so on, integer. So we see that if we take r to be constant, that means the angle r at which light falling is constant, then the fringes are observed for various values of d. D means separation between the mirrors. Or more general, if this distance is d1 and this distance is d2, then obviously d is just equal to d1 minus d2 or d2 minus d1 as the case may be. One important thing here, that the light traveling along y-axis crosses the beam splitter twice, once going and coming up, while the beam traveling in x does not cross the beam splitter twice. Therefore, we put a compensating plate, a plate identical to the beam splitter, but which does not reflect light, and therefore this path difference due to passing through beam splitter is compensated. This plate is known as compensating plate. This compensating plate is not a must while observing interference with white light, with monochromatic light, but it is a must if we want to observe interference with white light. Obviously, let us see how do we get the fringes and what type of fringes shall we have. So let us consider these two mirrors here, mirror and image of the mirror, namely M1 and M2 dash. The light traveling here, being reflected, see that for cos r to be constant, we shall find that this cos r remains constant on the circumference of a circle. The value of r remains the same because film thickness is same everywhere, so cos r remains constant, and therefore the locus of cos r is equal to constant is a circle. Therefore, we shall observe circular fringes, concentric circular fringes, concentric circular fringes. The important thing here is that these fringes correspond to the constant inclination, and therefore these fringes are known as fringes originating from the constant inclination of the beam. These fringes were observed first time by Hedinger, and therefore they are also known as Hedinger's fringes. We can now compare these fringes, which are circular in nature, with the circular fringes obtained in Newton's rings experiment. See that Newton's rings fringes originate from the locus of constant thickness of the fringe, and therefore they are the fringes. Newton's rings are the fringes originating from constant thickness of the film. These are known as Fizeau fringes. So there is a substantial difference in the origin of Newton's rings and the Michelson rings. Here the air film, here the film through which we are observing interference is real in case of Newton's rings, but the air film in case of Michelson rings is virtual air film. It is not air film. Since the interfering beam in Newton's rings is a diverging one, that means image will be formed in the plane of the film. Therefore, Newton's rings are localized rings. They are localized in the plane of the film, whereas Michelson's rings, the two beams are parallel. We are using telescope and they are observed at infinity, that means at the focus of the crosswire of the telescope. And therefore, to observe Newton's rings, we need a microscope, but to observe Michelson's rings, we need a telescope. That is another difference, and few more differences will come out as we go through this entire text. Let us now discuss the origin of circular fringes in Michelson's interferometer. We know that locus of cos r is equal to constant is a circle, therefore the fringes are circular. Let us see what shall happen as we move one of the mirrors to change the thickness of the film, air film. Suppose we consider d equal to 0, that means d1 minus d2 equal to d equal to 0. That means the mirror M1 and the image of mirror M2 are coincident. In this case, the thin film has 0 thickness, but there is a path difference of lambda by 2 due to reflection of one of the beams from the denser medium, and therefore net result will be a destructive interference. The entire field of view will be dark. Entire field of view will be dark. Suppose now we move one of the mirrors. Suppose we are moving one of the mirrors. This mirror we are moving. Then suppose D1 minus D2 is say lambda by 2, lambda by 4. That means 2D will be equal to lambda by 2, and net path difference then becomes lambda. That means there will be a constructive interference. We are observing normal incidence. Normal incidence. That means R is equal to 0. We are discussing how the fringe pattern changes when we move one of the mirrors. And therefore, when we move the mirror through a distance lambda by 4, the net path difference created between interfering beams is lambda. They will undergo constructive interference. As a result, the center of the ring pattern will become bright and rest remains dark. The center becomes bright. Suppose we move the mirror further. D1 minus D2 is say lambda by 2. That means we have moved the mirror further by a distance of lambda by 4. Then what shall happen? The net path difference will be 3 lambda by 2, and consequently the center of the ring system will become dark, and this bright will be thrown away and then dark. So what we find that now there will be a dark at the center and a bright ring will be thrown away a little away. Next, let us move the mirror further, and D is equal to say 3 lambda by 4. Then the path difference becomes 2 lambda. Consequently, at the center, I shall have a bright fringe, bright ring. The dark ring will be thrown away a little more, and that will be the ring pattern. So what we see, as we move the mirror, that means as the separation between the mirrors is changed, the center becomes alternately bright and dark. Number 2, whatever ring existing at the center is moved away from the center, and as we go on moving the mirror, the rings will be originating from the center and occupying the space again and again. Now, interesting thing, when we look obliquely, then R is not 0, then R has a finite value. The net path difference is say 2D cos R. So as we increase D, for the particular R, N increases, higher order rings appear. Fine. Next important thing, suppose because D is constant, the distance between the mirror separation is constant, then as we increase cos R, or as R increases, cos R decreases, so N decreases. Therefore, very interesting to note that the ring at the center will be of the lowest order and the ring at the circumference will have highest order. Repeat, I repeat it, this is very important. As R increases, cos R decreases. As R increases, cos R decreases. Therefore, N decreases. Therefore, the ring at the center will be of the highest order ring and ring at the circumference will be lowest order ring. This is just reverse of Newton's rings. In Newton's rings, we have zero order ring at the center and higher order ring at the circumference. Since the ring at the center is not known of what order, therefore, to put this instrument to experimental measurement, this formula 2d cos r is equal to n lambda will not serve the purpose. We have to work out a formula which can be used practically. Therefore, what do we do? Let us consider a ring pattern. This is of course not to the scale diagram. The ring at the center, we renumber it. We renumber the ring at the center and we call it as a mth ring. At the center, it is of say 0th order ring. Then the next ring we call as the first ring, then second ring and so on. Since originally the ring at the center was having nth order, we don't know. It was of nth order and we have called this as 0 order. So what shall happen? The first ring which we are calling will be n-1 ring, m-1 ring, and the second will be m-2 ring and so on and so forth. Now we can count, say we call this as mth ring. So mth ring will be equal to, mth ring will be ring at the center minus mth ring, nc minus mth ring. We called nc, the ring at the center. So any order ring we call them, now we have renamed the ring at the center, we call it 0 order ring, then first ring we call, that will be nc minus 1, sorry, the next ring will be nc minus 2 and mth ring will be nc minus m. I repeat it again, we call the ring at the center which is originally nc as the 0 order ring. Then the first ring we are calling will be nc minus 1, the second ring we are calling will be nc minus 2 and so on and so forth. So mth order ring will be nc minus m. Now we use this information in the original formula. So at the center, r is equal to 0 and therefore 2d is equal to nc lambda. And for mth ring, 2d will be equal to 2d cos r will be equal to nc minus m into lambda. Because the mth ring we are calling is originally nc ring. Subtracting second equation from the first, 2d 1 minus cos theta, cos r, or we can call cos theta, doesn't matter, equal to m lambda. This is the formula which will be used in calculating various parameters relating to Michelson's interferometer. I repeat it, 2d cos r is equal to n lambda is the original formula, but we have seen that as r increases, cos r decreases, therefore n decreases. Therefore, the ring at the center is of highest level, r equal to 0 means cos r maximum value. So ring at the center is of highest order and ring at the circumference is at the lowest order, but order is not known. Therefore, we have renumbered the rings. We call the ring at the center to be of say 0 order, then first ring, second ring, third ring, fourth ring. Then our mth ring will have an original order of nc minus m, which we have used in the formula, and we have found out the formula 2d bracket 1 minus cos r bracket closed is equal to m lambda. This is a workable formula, and now we number the fringes from 0, 1, 2, 3 starting from the center. Suppose we started that we call the ring at the center as the first order ring, then this formula will be modified and we will have m minus 1 into lambda, because one order less and nothing will change, everything will remain the same. Now let us see how can we measure wavelength of light. A few important things I must say, that cos r varies non-linearly with angle, whereas d varies linearly, and therefore the rings appear at the center at a faster rate than rings disappearing at the circumference. Therefore, the ring pattern will be such that the rings at the center will be quite thick and the rings at the circumference will be quite thin, as in case of Newton's rings. This is similarity between Newton's rings and Michelson's interferometer rings. Now let us proceed how to measure wavelength of light. The answer is very simple. For the rings at the center, 2d is equal to n lambda for dark. You see, there is another difference between Michelson's rings and Newton's rings. What is that? The center of Newton's rings is always dark, but the center of Michelson ring may be bright or dark depending on the separation between the mirrors. This differentiates Newton's rings from Michelson's rings. Now coming to here, 2d is equal to n lambda. Now if we can vary d, then variation in d can be noted and corresponding variation in n can be noted, and it is possible to determine wavelength of light. So for this, let us come out with the Micelson's interferometer. So to arrive at Micelson's interferometer, we just draw a diagram of Micelson's interferometer. This entire system is located on a rigid platform, very rigid platform. Mirror M1 or M2, here mirror M1 is made movable by mounting it onto a carriage. Before this, it is enclosed in a box with 3 leveling screws like this. This is a mirror and there are 3 leveling screws which are located on the vertices of a right angle triangle, so that this mirror can be tilted in any plane they like. Why this is required? Because to set Michelson's interferometer into operation, the beam should fall normally onto the mirror. This is very, very important and a stringent requirement. Similarly, the another mirror is also put in a box with 3 leveling screws. This system is mounted on a carriage box, and this carriage box is finally mounted on a movable screw fitted with rank and pinion arrangement. There are gradations on the circular scale also. So as we move this screw, the mirror moves back and forward. This entire system is rigidly fixed. So the mirror is made movable. Exact diagram is shown in a slide separately. So what do? We note the position, say, a darkening at the center, darkening, nth darkening at the center, and we read the micrometer screw. Say it is x1. Now it is moved. As it is moved, the center changes to bright, then center changes to dark again. That means 1. Next time dark, 2. Third time dark, 3. And so on and so forth. So we start going counting the rings, say n plus 50, then n plus 100, then n plus 150, and so on and so forth. And corresponding readings we note down. We found out the mirror movement for the escaping of 50 fringes. Then we subtract x3 minus x2, then x4 minus x3, then x5 minus x4, and so on and so forth. We average this. This average x will be for 50 fringes. So for we use the formula, so 2x bar is equal to 50 into lambda. The wavelength can easily be determined. It is a straightforward, very simple technique and a very accurate result, because the least count of this instrument is quite small. The next application, which is of course very important, is to determine the wavelength separation between two closely spaced wavelengths, spectral lines. Determine the wavelength separation between two closely spaced spectral lines, say D1 and D2 lines of sodium. Now this small wavelength separation has a very, very important repercussion. How to determine the wavelength separation between the two waves? 2-3 things should be clearly understood. There cannot be any interference between the waves of different wavelengths. Therefore, the two wavelengths, say lambda 1 and lambda 2, shall form interference patterns separately. They will form interference pattern independently. However, because the wavelength difference is quite small, the pattern will look almost the same. Then, since we are observing through a telescope, these two interference patterns will get superimposed. Now there may be a situation that the maximum interference pattern due to lambda 1 coincides with maximum interference pattern of lambda 2. In that case, we will have the best contrast. However, in case when maximum due to lambda 1 and minimum due to lambda 2 coincide, we will have worst contrast, because the maxima will cancel with minima. Almost uniform intensity will be observed. Therefore, what shall happen when we move the mirror? When movable mirror is moved, a stage will reach when the maximum due to lambda 1 will coincide with maximum due to lambda 2, and we will have best well contrasted rings. When we move the mirror further, the contrast will go off and a stage will be reached when distinct rings could not be seen. We continue to move the mirror, we will come with again a situation in which we will be observing best contrast again. We use the situation of these two best contrasts to find out the separation between the closely spaced spectral wavelengths. Say in the first case, 2D is equal to NC1 lambda 1 is equal to NC2 lambda 2. Next best contrast. This is first best contrast. Suppose we have moved the mirror through a distance x, then obviously NC1 plus N lambda 1 will be equal to NC2 plus N plus 1 lambda 2. Why? Where lambda 2 is less than lambda 1. Why? Because the best contrast will be observed when we have a difference of exactly one wavelength. As we proceed, lambda 1 is greater than lambda 1 is greater than lambda 2. See, these are the fringes due to lambda 1. And these are the fringes due to lambda 2. Lambda 2 is less than lambda 1. Therefore, this goes on shifting, 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 and a stage will be reached when N plus 1 fringes will fall in the same distance as N fringes of the larger wavelength. Subtracting this equation, say one equation, and this is two equation, then 2 minus 1 will lead to 2x is equal to n lambda 1 is equal to n plus 1 into lambda 2. Or lambda 2 upon lambda 1 is simply equal to, or lambda 1 upon lambda 2, lambda 1 is bigger, lambda 1 upon lambda 2 is n plus 1 upon n. This is equal to 1 plus 1 upon n. So lambda 1 minus lambda 2 upon lambda 2, this is equal to 1 upon n. Therefore, we use this in this equation. Again we use in this equation value of n. So 2x will come out to be, n means lambda 2 upon lambda 1 minus lambda 2 into lambda 1. Since lambda 1 is quite near to lambda 2, therefore lambda 2 lambda 1 can be equated to lambda square, and therefore 2x is equal to lambda square upon lambda 1 minus lambda 2. And finally, we are in position to determine lambda 1 minus lambda 2 is equal to delta lambda is equal to lambda square upon 2x. Since x is known to us, lambda we have already determined earlier, therefore it is possible to determine the separation between the wavelength of closely spaced spectral lines. One thing may point out here, the essential condition for observing interference is the coherence. That means two waves should maintain constant phase difference. There are two types of coherences we use in practice. The concept of coherence is unique. However, to have simplified experimental versions, we use two types of coherences. One is the spatial coherence that refers to the waves propagating side by side, just as in case of Young's double slit experiment or biprism experiment. Another is the temporal coherence that refers to the waves propagating in the same direction, and this temporal coherence is related to monochromaticity. Monochromaticity means how far the wavelength remains constant, and therefore delta lambda measures the deterioration in coherence, or we can say coherence is temporal coherence. Temporal coherence is inversely proportional to delta lambda. We also call lambda upon delta lambda as quality factor Q. This is the Michelson interferometer we are using with ordinary light and used in undergraduate laboratories. In the advanced laboratories and postgraduate laboratories, the source, sodium lamp source, is replaced by a laser. And the mirrors and beam splitters are also compatible with the laser beam. And therefore, we call that as laser Michelson interferometer. That instrument is versatile and frequently used in optical technology. We can measure the thickness of thin film using Michelson interferometer, or alternately, if thickness is known, we can measure the refractive index of the film. This measurement is very important in the designing of VSLI, very large scale integrated circuit design. Okay, let us consider a thin film of thickness T and refractive index mu. The light is falling normally and crossing it. The important thing is we put this film into the path of one of the arms of Michelson's interferometer. Since the light traveling through medium has less velocity than air, therefore the light ray passing through the film will be delayed as compared to the light traveling in another arm. Let us see how much path difference does this introduce. Suppose the light time taken through film will be just T upon velocity in the film, and time taken in air T0 will be T upon C, where V is C upon mu. Mu is the refractive index and C is the velocity of light in air. Therefore, the time difference created will just be equal to delta T is equal to T minus T0. That means T upon V minus T upon C. Path difference will be just C times the time difference, will just be C times the time difference, and therefore C T upon V minus C T upon C, this is equal to T into mu minus 1. Since the path difference of lambda shifts the fringe by 1, and therefore the number of fringes shifted will be lambda path difference divided by lambda. This is equal to, say, number of fringes shifted n. Since the number of fringes shifted is known to us, we can calculate the thickness of the film here, or alternately we can measure refractive index of the film. The another aspect here is that if we use monochromatic light, the fringes are identical, and it will not be possible to ascertain the shift in the fringes. To ascertain the shift in the fringes, we use white light. And second variation we do is that we tilt this mirror slightly, therefore the two mirrors are no more parallel, but they form a vase-shaped film, and fringes becomes localized. See, since the basic formula is 2d cos r is equal to n lambda, therefore higher order rings will be located at less radius. That means that will be the situation. The rings will look like this. If the mirrors become plane like this, crossed like this, then they will become straight line fringes. If this mirror is coming down, I am sorry, I have located it wrong. This is this and this. And if this happens, then the ring pattern will become like this. So it is possible by selecting the pattern between this and this as a straight line pattern. When straight line fringes are formed, the central fringe will be white and all other fringes will be covered, and therefore it is possible to ascertain the shift in the fringes when we insert a thin film in the path of one of the beams. And therefore from the shift in the fringes, say the shift is x delta x, then from that shift the corresponding path difference will be 2 delta x, then 2 delta x divided by lambda will give me n, the number of fringes shifted, and from that I can calculate the refractive index or the thickness of the film. The most important application of Michelson interferometer in optical technology is to test optical devices. Almost all devices can be tested with this setup. Of course, we use the source as laser and all the optical components compatible to that laser. Suppose we want to test whether the plate is optically plane or not, then we put this plate in the path of the Michelson interferometer. If it does not disturb ring pattern, that means the glass plate is an optically plane glass plate. Suppose we want to test prism, then we orient the prism and we put another mirror which reflects light normally. If the fringe pattern remains absolutely circular, that means the prism is a perfect prism. If there are distortions, that can be find out that which surface is not working well. We can identify all the three surfaces of the prism. Suppose we want to test a lens, whether lens is a perfect lens or not. Are these curvatures perfect or this surface is perfect? We put a lens and a reflecting mirror behind that reflects light normally, and this system is put between one arm. If the ring pattern remains perfect, nothing changes, then device is perfect. If the ring pattern changes, then what we generally do, we take a section of this lens where there is no change in ring pattern, we mark that section, we cut out that section and use in the instrument. So this is Michelson interferometer. This is a very versatile equipment. Dear friends, this here completes this second part of interferometer, but I may point out that interference is a very, very important phenomena, and the most important application of interference is in holography, three-dimensional photography. In a holography, what do? We take a photograph in a given light and we superimpose on that light the reference beam, that means a part of the beam taken out, and thus image form is nothing but an interference pattern. When this pattern is illuminated by reference beam, we see the image. Not only one image, but one real image and another virtual image. And this is a hologram. Therefore, the most important application of interference is not only in instrumentation, but in practical applications as holography. Thank you very much.